In this video, we are going to talk about the kinetic energy of molecules in ideal gases. But first of all, in this slide, let's look at some properties of ideal gases. So what do we mean by saying ideal gas? Well, in the ideal gas, the molecules are far apart from one another, and the separation distance between them is much greater than the diameter of those molecules. So, and if we have this property, then we can check this property, and then the molecules should also obey the laws of classical mechanics. And the third one is that the weak attractive forces between molecules are negligible. And as you know, we all know that the molecules have some attractive forces between them, like electrons of one molecule are attracting the, there is a attractive force between the electron of one molecule and the nucleus of another molecule, so they will attract each other. But for the sake of these ideal gas properties, we need to ignore these proper forces. So we can say the third mark is also satisfied. And the fourth one is that collisions between the molecules are perfectly elastic. And the duration of collisions are very short. And it's like the collisions are happening in an instant time. And it is very short period of time. It is like a billiard balls. When you can see billiard balls, when they hit each other, the duration of collisions are very short, and they completely bounce from each other. So you can say the fourth criteria or property is also satisfied. So now let's look at the another stand and continue our lesson. Okay, in this slide we're going to reach and conclude to the important formula in the kinetic theory of gases. And let's consider a container like which I drew here, and it is like a square cube, and this cube has some gases, some molecules inside it, and all of them are colliding each other and moving randomly around. And let's assume one molecule, and this one molecule, for example like this, is moving horizontally and it parallel with the x-axis, and it has a velocity and also of course momentum. So it has just x component, so its velocity has just x component, no y or no z components. And first it moves in the minus x direction, so its momentum will be minus mvx at first, and then it will collide to the wall of this container, and it will bounce and it will move to the opposite direction. And since there is no attractive forces between these molecules and walls, and the collision is perfectly elastic, we can use the third law of Newton's, Newton's law, and we can say the change in the momentum, I mean the delta, let me write it in black, the delta mv, which is the momentum of this molecule, is equal to mvx minus mvx equal to 2mvx. Because at first, let's say this is the P2 minus P1. So we had momentum. At first it was minus mvx, and then it is mvx, the P2. And as we know from the second of the Newton's law, we have F equals to the derivative of momentum with respect to time. So this is the important thing we need to know. And also, if we look at this picture, this molecule should go back and forth, and it will travel a distance of 2L with the speed of Vx in the time of delta t. So we can say 2L will equal to Vx times delta t. And from here, the delta t, the time it takes for this molecule to return to its position back again, it will be 2L over Vx, right? So we know this. And from here, if we substitute this information, we can say also F is equal to delta mv, which is the momentum, over delta t. And if we substitute the delta t, which we found, it will be 2mvx over 2L over Vx. So if we calculate it, it will be mvx over 2 mvx square over L. So this is the force due to one molecule that exerted on the wall. So this is very important thing to note. Also, this is, you may say, okay, we just consider the x components, not the y or z components. Yes, you're right, but this molecule, during its passage back and forth across the container, the molecule may collide with the tops and sides of the container, but it doesn't change its x component of momentum. So it does not alter our result. It may also collide with other molecules, which may change its Vx. However, any loss or gain of momentum is acquired by other molecules, and because we eventually sum over all the molecules, the results, the effect will be included. So don't worry about it. So this is just for one molecule. So we know that in the container, we have many molecules. So we need to consider them as well. And if we want to consider them, we need to sum all of the results together. So the average force will be m over L times Vx1 square plus Vx2 square plus until Vx n square. But what do we mean by Vx1? Well, Vx1 is just the x component velocity of the molecule number 1, and Vx2 is for molecule number 2. So this is the meaning that we're going to say. And also, if we look at this, and we can say the sum over the total number of molecules n in the container, the average value of the square of x component of velocity is, I mean, what do we mean? We can say that Vx square mean, the mean of the square of Vx is Vx1 square plus Vx2 square until Vxn square over n. N is the total number of molecules. And if we want to put this Vx, the mean of the square of Vx, to our formula to here, so we will have F equals to m over L n Vx square, the mean of the Vx square. So we know this, right? Okay, so we got this formula. And now, from the theorem of Pythagoras, we know for any vector, the square of any vector, I mean, v square equals to its x component square plus y component square and plus z component square. So we know this, and so it is clearly, we know that the mean of v square is this expression. And also the velocities of the molecules in our gas are assumed to be random. We can say Vx square, the mean of Vx square is equal to Vy square, the mean of them, and also for the z component as well. So because it is completely random, there is no preference of the direction. So this expression should be satisfied. Okay, this expression. And from here, from these two, we can say v square, the mean of v square, it will be 3vx, the mean of 3vx square. So we find this, and if we put this expression to our formula, the f will be, to this formula, the f will be m over L n v mean of v square over 3. So we will find this, we will get this formula. And this is the average net force of the molecules that are exerting on the wall. This is very important. So now, after knowing this formula, we can also find the pressure. The pressure P is just equal to the force over the area. So for our wall, we can say it will be 1 over 3. If we use this formula that we got, it will 1 over 3 times n m mean of v square over al. And al is a times l is just the volume, right? So we can write like this. Okay. Now we know this formula. This is very important formula that we need to know. And then by the laws of the ideal gases, we know that PV, let me write it in another color. PV, the pressure times the volume, is equal to nkt. This n is the number of molecules, the number of molecules. This k is Boltzmann constant. And T is the temperature. Okay, so we know this from the laws of the ideal gases. And what do we get? And here, we can move V to the other side. So we will have PV equals to 2 over 3 n times 1 over 2 m mean of V square. We get this expression, okay? And this is also equal to what we got from here, right? So we can write it as nkt. And if we simplify them, then we will get 2 over 3, and these n will cancel each other. 1 over 2 mv square equals to kt. And what we notice from this expression, this is just the translational kinetic energy. This is the big K. Right? Don't confuse it with this K, this little K. It is the Boltzmann constant. So they are different. So we can say K. I put the bar because it is the average, equals to 1 over 2 mv square equals to 3 over 2 little k then t. So this is the most important thing that we need to know in the kinetic energy of molecules in the ideal gases. So what this formula tells us is that the translational kinetic energy of molecules in random motion in an ideal gas is directly proportional to its absolute temperature. So this is the temperature, and this is the kinetic energy, and so they are directly proportional to each other. That's why when you increase the temperature of a substance or of a gas, the kinetic energy, the internal kinetic energy of those molecules will also increase. And that's it. I hope that this interesting formula is helpful to understand more deeply the concept of kinetic energy of molecules. Thanks for watching.